Welcome back to this TA session, and this time we are going to look at some new topics, new um, um, phenomena of biological processes, which is charge flux. So, as usual, before starting, we would give around 5 to 10 minutes, 10 minutes perhaps, for people to join, and then we'll start. So, basically, today we are going to talk mostly about light. Uh, in fact, entirely about light. Light, as you know, is an electromagnetic radiation where the electric and magnetic fields are orthogonal to each other. And yeah, we'll talk more about that. Let's wait for some time right now. All right, let's start. So, as I said, it's going to be about electromagnetic radiations today. I mean, whenever a charge flows, when there's a flux of charge, it has an electric and a magnetic field associated with it, assuming that the rate of change of electric field is there. So, but when you say an electromagnetic field, the first thing that comes to your mind is the thing that happens every day in the morning at around 6 o'clock, right? I mean, when the sun rises, everything gets lit up, and that's light. And this is the image of the day of the James Webb Telescope, showing some nebulae, nebula or nebulae, I don't know. I think it's nebula. Sorry, I think one star. It's one nebula. I don't know how many stars are forming in here, but it is basically the light that is being captured from these images, and what you see as nice red color thingies here is basically clouds of dust and smoke, dust and gas, emitting copious amounts of ultraviolet radiation that would mutate every cell of your body if you're anywhere near it. So don't go near a nebula, that's one thing. But when you think about light, in addition to it being electromagnetic, is there any other way that light can be described as? We say it's an electromagnetic field, alternating electric and magnetic forces, photoelectric effect, solar panels, etc., etc., etc. These are physical phenomena. But what do you observe from uh, this beautiful picture from the James Webb Telescope? Just give a minute of thought to it. In addition for light having electromagnetic properties, is there any other way in the context of this picture, or in the context of pictures of telescopes, that of pictures of images of galaxies some a few hundred or even thousand light years away, or nebula in this case, what does it represent actually? Let me twist the question in a way that might give you a hint. So let's assume that this is some 600,000 light years away. Do you think this picture that we have right now would be the picture? This is a nebula that is there, and do you think that this nebula would be the same right now? If you get the answer to that, you might think about light as a different type of a source. Just think about it for a minute or two. I'll give you a minute or two. Think about the distance that light has to travel. Light years is not number of years, it's the distance. One light year is defined as the distance traveled by light in a year. Correct? So, yeah, that's another hint. Think about it and let me know. Beautiful nebula, right? It's a pity that these are all ultraviolet radiations. It looks like a place where I can take a vacation at. Beautiful mountains and a lot of stars and stuff, but such is life. All right, I'll give you the information. So, in addition to it being electromagnetic in nature, light is also a source of information. Correct. So, taking our assumption of around 6,600,000 light years, which means that light has traveled. So, this information about this nebula has traveled so much of a distance to be captured by the James Webb Telescope. Correct. James Webb Telescope, correct? So the point is this, right? So it took light around 600,000 years to come and be captured by this telescope. So this piece of information that you're seeing right now is the picture of the nebula that was, you know, not in our years, but it was in a sense, if uh, uh, we can say that as this was the nebula around 600,000 years ago with respect to the speed of light. So we don't know whether this nebula even exists right now. So we don't know what is the fate of this nebula right now as we speak, because this is an image that is around 600,000 years old in terms of the light coming from this source. So, if you think about it, I mean, the stars that we see on a clear night sky, they are all coming light years away from, right? I mean, millions of light years away. Some stars are millions of light years away from us, and the star that you see right now might not be there. Actually, what you are seeing is just an illusion, and the philosophical implications of all those things put aside, we can think of this universe as a giant USB drive, which is a store of memory in a way. And in the minuscule lifespan of around 60 to 70 years, we are looking at this, or we are being conscious of this phenomena of this giant USB drive in in one way or the other. And I wanted to dwell on this. I wanted to you know give you this idea of light being a source of information. In addition to it being what it is, it's not only physical in nature, it's informative in nature too. Now, coming to charges or electromagnetic um, or the electromagnetic implications of a charge stored and the gradient of charge. So when you go through the lecture as well as the book, you should be familiar with the terms of charge density, etc., etc., etc. So charge density is the charge enclosed in a unit volume, and the charge density in a volume element, and the charge density into the total into the volume is the current. So that's how it's been defined here. Sorry, the charge density times the volume is the velocity of charge is a current. So basically, current is the rate of change of charge per unit time, correct? And the charge density, the net charge in a volume element divided by the time divided by the volume, and I equal to d rho by dt equal to p into velocity vector, because the higher the velocity, the higher is the rate of change of current, correct? The charge is moving faster, there is a higher rate of change of current. Now yeah, so we are going to look at Maxwell's relations and the Lorentz relation. But before that, we will be looking at this diagrammatic representation of what we will be looking at mathematically in all these relationships that I just said. The contour. So basically, a contour is a complex shape, and there are two things here. One is the um, think of this thing in a three-dimensional way. Okay, I mean, see, there are two vectors here. One is the s vector and the a vector, and here it's given as ds and dA vector elements, let us say. One is along the surface of the contour. So basically, the line surface of the contour, if you just move in a along the plane of the complex object, if you can say, yeah, that is the ds vector. It's along the surface, and the dA vector is normal to the surface, normal to the plane of the contour. So keeping these in mind, we now go to the Lorentz law and the Maxwell's relation. So basically, Lorentz law tells us the force that's being exerted on a charge that is moving with the velocity v, and which is represented by the vector v. So it's basically E vector plus V vector into mu naught into H vector, which is E is the electric field and H is the magnetic field, and mu is the permeability of free space or vacuum. Um, so uh, I want this to be as like kind of a ready reckoner for you people to just look at these relations, and uh, the uh, the relations are better explained by Dr. J.K. Sir in in his lecture videos. So in addition to uh, you know uh, um, um, looking at this video, please look at the videos. I mean, I'm sure you would have. And this is just a ready reckoner, for formula sheet, if I may say so, for you to straddle through your assignments in a easier way. Again, the assignments doesn't it's not a big deal actually. It's again mapping formula to questions. Simple assignment. So I would more than the second thing is that in addition to this being a ready reckoner, I would also like you to understand what these things imply actually. The first Maxwell relation is a relationship between the charge enclosed in a volume and the electric flux through the surface. So what is it? So let's take a box, and that box has a volume element, and let's say that volume element is dV, and we know that rho is the charge density, and so basically the charge stored in the volume is the charge enclosed in that volume element is rho times dV, and what you see here is the surface integral of the electric flux through the surface. So basically, electric flux is all the fluxes that you have seen. Diffusion. I mean, it's defined in terms of per unit area, and what it says this equation says is the relationship between the charge enclosed in the volume and the electric flux in the through the surface of the volume element. So mathematically you can look into this. I mean, it's just epsilon naught is the permittivity of free space, and rho dV integrated over the whole volume V gives you the total charge in the in the total volume of the box. In other words, it basically says that the total volume in a box is equal to the electric flux that is moving through the surface. So it makes sense, right? I mean, the more electric flux is there, uh, think of electric flux like all other fluxes, right? I mean, um, if you want to have an analogy here, if I can give you, um, No, I think analogy would complicate matters further. So basically, it's intuitive, right? The more electric flux the more electric flux that is through a surface per on a given per given time, the more charge, the more is the propensity of that block of um, object to store charge. Think about a capacitor, correct? So the more electric flux that you give it, I mean, the more charge it will store. It's not a like to like comparison. Don't hold me to that, but I think you get the gist of it. You should have by now. Now let's come to the Maxwell's second relation, the relationship between the magnetic field and the charge flux. So whenever I would like to note something here. So whenever there is flux, it is always denoted in terms of the area, and whenever it is in terms of field or field intensity, magnetic field intensity or electric field intensity, as we will see in the third relationship, it was denoted in terms of the surface vector. So as we saw here, the surface vector is along the surface of the uh, contour of the object, and the area, the area vector is normal to the surface. These things, you have to. I'm just brainstorming here. If you go through the lectures in NPTEL, you would easily understand this. So the relationship between the magnetic field and the charge flux is given as the sum of the current. So basically, this is a contour integral, and this is a surface integral. Okay. So the magnetic field intensity, which is given by this term, is equal to the sum of the current and the time rate of change of electric flux. We can also call this rate of change of electric flux as the displacement current, and the unit for displacement current is also amperes. So this integral, intuitively, if you integrate over the area, it gives you the current. So this is the time rate of change of the electric flux. Electric flux is given by, as you can see here, this is the electric flux, right? The surface integral. If you see, the both terms are similar, and that is that's how it is. This is the second relationship. So I'm repeating again once more, the relationship between the magnetic field and the electric charge flux is basically, it is the sum of the current. If you want to see it in terms of this, take a small if you take a small surface element, and the ds vector element and the da vector element in that surface element, this is the relationship between the magnetic field and the charge flux. It is basically the sum of the current and the time rate of change of electric flux, which is also called as the displacement current. Now coming to the third relationship. So now see here it was electric flux, sorry, charge flux, and that was, it was given as dA. Now it's electric field. Now electric field is given as ds, and magnetic flux, so it is given in dA. Here it was magnetic field, it is given in ds. So these are all, easy ways to remember these otherwise abstruse formulas. So the relationship between the electric field and the magnetic flux is basically the contour integral. As you see, this term is equal to the negative time rate of change of this term, and that is the Maxwell's third law. Now, third relationship, and coming to the fourth relationship. So basically, what it says is the magnetic flux of an object is only within the object. There is no magnetic flux outside of the object. If it's enclosed by a surface, it starts there, and it circulates there and it ends there. So this is basically the surface integral of mu naught into h into dA. So net magnetic flux out of a region enclosed by a surface is 0. So these are the four relations of Maxwell. And there is a principle of charge conservation. Now, assuming that, I mean, if you look at the book and the lecture, you know, you will see that, you know, this is first given as, you know, surface integral of IdA is equal to the negative of the time rate of change of the electric flux. So what it says is this. What it means is this. So let's take a volume element. You know, if there is no addition or subtraction of charge within the volume element, we take the volume element with the charge as is, and there is a, you know, there's a current that keeps going out, that should be equal to the decrease in the decrease in the charge per unit time, or which is represented by this uh, by this term, the time rate of change of electric flux over the area. So the higher the current, the lower the or the higher the depletion of charge within the volume element, or in other words, high, we can also say that higher the rate of change of the electric flux over the area in a negative way, so then it should be lower. Okay, fine. So that's how it's defined, and so you take this term this side, you know, this plus is equal to 0, and then if you go into this in detail, you should these integral terms are uh, substituted as in terms of phi, and I don't want to go into that. Those are apparent, they are in the textbook as well as in the lecture. Please go through that. Now all of this is in integral form. Okay, so we need to change it into differential form, but there is one problem. The problem is this, right? So in some cases it's a surface integral, and in some cases it is a contour integral, and whenever it is a contour integral, it you have the term ds here, and whenever it's a surface integral, you have the term dA here, right? So how do you arrive at the above solution? So basically something, so these contour integrals must be changed, right? I mean these contour integrals must be normalized either in terms of ds or dv, you know so how would you do that? So I would not give you the answer right now. I would suggest you go and look at the lecture. There are two things here. One is the Gauss's law, and the second one is the Navier's law. Sorry, yeah, Navier's law, Stokes law or Navier's law, I forget, but one of this law. So that gives you a means to convert the surface integral into a volume integral, and a contour integral into a surface integral, and once you do that, I'll give you a hint. So if this is converted into a volume integral, so this volume element is arbitrary, right? I mean, dv could as well be v, and rightly when I started the lecture, I said that integral p rho dv integrated over the whole volume v is equal to the charge q in the total volume of the box. So basically the volume element is arbitrary, and if on both sides, it's integral over v, we are not cancelling the integral out. Please don't think it like that. All I'm trying to tell you is that the volume element that we are taking is arbitrary in nature, and this volume element dv could as well be v, but typically it's not taken as that because the v starts from the first principles of calculus. But for the for the conversion of Maxwell's relations into the differential form, we in effect cancel out the integral over v on both sides, as well as the surface integral when you look at the Stokes law. So I would stop at that. If you have any further doubt on this, I would suggest you go and look at the lectures and read the book. It's actually quite simple. Now let's now talk about a very interesting phenomenon that is the pseudo steady state of, or the pseudo steady state that exists between light and biological systems. Uh, well, I think it's too. I hope it's not too much for you guys. I mean, all these formulas, you're not intimidated by this. It's just formulas. um, if you have any doubt in these formulas, I suggest you look at the lectures in conjunction with the text of the book Continuum Analysis in Biological System. It's very easy to figure out if you do it that way. And okay, let's go to the pseudo steady state. As you know, pseudo steady state is pseudo steady state has been explained well when diffusion was discussed in terms of, you know, a car assembly line. It's simple, right? If the rates, if we take two different phenomena and we are trying to understand the relationship or the interaction between these two phenomena, these two systems interact in one way or the other, and the rate at which one system operates is far different. I'm talking about orders of magnitude different from the rate in which the other interacting system, you know, behaves. We can say that these two combination of systems is in pseudo steady state. I'm repeating this again. If we take two systems, and if one system and we are trying to study the interactions between them, the rate of and the rate at which system 1 behaves is orders of magnitude different than the rate at which the system 2 behaves. And when these two systems interact, these two systems are said to be in a pseudo steady state. This is a scientific explanation of this. For a more commonsensical explanation of this, or a refresher of this, I would suggest you go and look at the video of, you know, it's just a 2-minute video. If you go to week 3 lecture, I suggest I will give you, 2 or 3 minutes time. You, if you want, you can just refresh your memories, there, you know, using that car assembly line, and juxtapose that with what I said, you know, in terms of the interaction between two systems whose rates are totally different. So I suggest you go look at that video and come back, and we will discuss this further. I'll give you 2-3 minutes, 5 minutes tops. Okay, one more minute. All right. So I hope you guys had that refresher, and if you now have the refresher, I'll just tell you this one. So there are two systems, system one, system two, and the rates of these two systems are interacting with each other, and the rates at which each system operates independently are different. These two systems interaction is said to be in a pseudo steady state. It's as simple as that. Now let's look at the pseudo steady state system of the light interaction of light and biological systems. As you see, biological systems is a system basically in a solvent. Water is always there, and the water has dipole moments. Water has the biological system inside the cell is there are charged particles and charged particles, proteins, DNA, whatnot. So how does light and biological system interact? For this, we have a pseudo steady state assumption. And how do this pseudo steady state assumption apply? So when you take the wavelength of light, typical light, right? Let's say um, what is the let's say the order of the wavelength is in the order of 10 to the power minus 4 meter, and um, the light is at the biological system that we are talking about. Its size ranges it's in the order of micrometers. So basically, there is one order of two orders of magnitude difference, right? So what happens actually is that what actually happens now? I've given you the definition of steady state. I'm saying that the biological cell length and the if you read this length scale of a typical cell compared with a length scale of an electromagnetic wave. So this is a small line, thick line here, and whereas there's a huge, it occupies a huge area. What does this imply actually? First of all, there are two questions. How can pseudo steady state be represented mathematically in this context? So if you see mathematically, the rate of change of the wavelength, or not the wavelength, the rate of change of the so basically wavelength is the fluctuating intensity in terms of the electric and magnetic fields, correct? So the rate of change of the electromagnetic field that interacts with the biological system um, is zero, right? So when the light whose order of magnitude is in the range of 10 to the power minus 4 meter interacts with interacts with a cell which is in the order of 10 to the power minus 6 meter, there is no change in the amplitude of whatever you are measuring. And in other words, there is no lag, or there is no you get instantaneous data. That's how you can put it, or in the text it's put even better actually. In other words, any fluctuation in times associated with cell interaction will not be noticeable at the scales of time associated with the wave. It's basically, Abel put out a line of what I just said. So, see, all these differential forms of Maxwell's, these are all in free space, right? It's epsilon naught is the permittivity of free space, which is also vacuum, and there's the permeability of free space. But when you are talking about biological systems, there is no free space. Actually, there is no free space. We are talking about a solvent system in which the biological system is suspended. Correct. So all these changes, how does it change? It's given in the text beautifully. I'm not going to go into that. You go look at how it is put. These equations and stuff like that. However, because of the pseudo steady state, all these equations changes dramatically. So how does it change? The first equation doesn't change. So first equation doesn't change except for the epsilon. But look at the other equation. So all the time rate of change, right? It essentially goes to zero. Look at the second and the third relations here. So three-dimensional operator into the magnetic field. Here it is I plus the time rate of change of the electric flux, but here it is just I. The time rate of change is not there because it's in a pseudo steady state. Similarly, the three-dimensional vector operator on the electric flux is equal to zero, and that's the beauty of the pseudo steady state, right? It just simplifies things and puts things into perspective. So what will happen if there is no pseudo steady state? Let us say that there is a change, the rate of change of the amplitude of wavelength is not zero. What will happen? Or if these two systems are not in pseudo steady state, what will happen? I'll give you a minute to think about it. Now I gave you the answer, so just a minute. It's simple, right? I mean, it doesn't go to zero. The time rate things don't go to zero, and you have to deal with these things, and you need to measure these things experimentally if you want to find it out. So that's how it is. So I'll stop here. I hope this was not a lot, and I hope you really enjoyed this discussion of light, as it being an informative source and us being a huge. I mean, what is huge? I mean, what is huge? What is small? I don't understand. It's just a pen drive of information out there. So just use the slides as a ready reckoner for getting the Maxwell relations and stuff like that. I mean, for a more detailed understanding of these, please go through the lectures of Sir, and please go through the notes from the book. Please go through the book. And in the off chance that anybody has come, I don't think so, nobody has come, and we are going to wait for another 5 minutes till the closing of the session for if anybody surprisingly crops up and asks a question. I would register it as the 8th wonder, perhaps write an application to the Guinness Book of World Records. Let's see. I hope people are going through these lectures, because we take time to prepare these things, and it would be good if somebody looks at these, listens to these lectures, or at least part of it, and posts perhaps a question in the channel or something like that. Okay then, I guess nobody has joined. Nope, nobody has joined. So I hope you have enjoyed this class, people who watch the videos, and as I said once more, it would be great if you watch these videos and post any questions. I'd be happy to answer that. Alright then, let's close it now. Thank you. See you then. Bye bye.